Hi and welcome to this short video on how do we write an electronic configuration for an element. So in this video, we'll be looking at how to quickly write out the electronic configuration for any element just by using the periodic table. Now in order to do this, we actually need a little bit of prior knowledge. So this is something that you'll be expected to know how to fill, which is always the lower energy orbitals before filling the higher energy one first. So in this manner, we actually write out the electronic configuration this way. So we always fill out the 1s orbital first, followed by the 2s, 2p, 3s, 3p, and instead of the 3d, we are actually filling up 4s first because it has a lower energy. Then we'll fill in 3d orbitals. Okay, so in this case, when we are looking at it, we can actually see that we are following this pattern here. We are following 1s, followed by 2s, 2p and 3s, 3p and 4s, followed by 3d. Okay, so that's how we are expected to write in our electrons. Now, in the s subshell, we have the s orbital, and that can hold 2 electrons. So it holds a maximum of 2 electrons. Same thing for the 2s subshell, right? It contains the 2s orbital, and that can hold 2 electrons as well. What about the p subshell? A p subshell actually has 3 p orbitals. Okay, and each of them can actually hold 2 electrons, which means that in total we are able to hold 6 electrons as a result. Okay, what about the 3s? Well, that is a s subshell, and s subshell contains just the s orbital, which means we are back to filling up 2 electrons. P subshell, very similar to the 2p, right? So this will fill 6 electrons as well, and s subshell fills 2 electrons, and d subshell is special. It has 5 d orbitals, and that means that it can fill actually a grand total of 10 electrons. So these are the maximum electrons we can actually put in for every one of our subshells and orbitals. So we're going to take note of this, and we're going to use this when we are filling up the electronic configuration of all the other elements. So I'm just going to make a little copy of this here, and we'll move over to your periodic table. Let's take a look at how the periodic table is actually arranged. We actually have multiple blocks of elements. So this is the first block of element that we can see, and this is actually what we call the S block elements. Why do we call these S block elements? It's because each of these elements end off with a S configuration. So here, for example, when we look at lithium, there are 3 electrons in lithium, and to fill that up, that will mean that first I'll need to fill in the 1s orbital with 2 electrons, and the 2s orbital with the remaining 1 electron. Let's take a look at maybe sodium, right? So this is another 1s2, this is 2s2, because we have to fully fill up the s orbital, and we'll be left with actually 7 electrons. So let's carry on with the 2p, and we are going to fill this up with 6 electrons, and that means that we have 1 left for the 3s orbital. So we can see that actually for lithium and sodium, they are both ending with a S1 configuration, and actually that is something that is true for the entire group 1. So the entire group 1 actually ends off with a S1 configuration. So what can we say about group 2? So for group 2, they actually have 1 more electron than their group 1 counterparts. In other words, instead of 3 electrons, I can add another one into the 2s orbital. And instead of 11 electrons, I have 12 for magnesium, and I can add another one into sodium. So that means that group 2s actually follow a S2 configuration. And that is why this is called an S block, because all these elements have a S configuration in their ground states. So let's take a look at another block here, and this is actually the P block. So the P block starts with boron, starts with group 13, and it ends at a noble gas, in this case neon. So we can actually write out the configuration we should expect: P1, 2, P6. So here's P4, P5, and P6. Okay, so let's take a look at how we can actually write the full configuration now. Remember that when we're writing configuration, we have to write the orbitals in ascending energy levels. So the lowest energy orbitals first, followed by the ones that are higher and higher in energy. So we're going to use the period number to help us as well, and I'm going to write the period number on the right. Okay, so this is period number 1, period number 2, period number 3. Okay, so let's take a look at carbon. Carbon we expect to have a P2 system. So we should expect it to end with 2 electrons in a P subshell. However, we also see that carbon is in period 2. So we'll actually be able to tell that carbon ends off as a 2p2 electronic configuration. So when we're using our shortcut, we can actually just write out all the electrons that are fully filled before we reach this 2p2. In this case, this will be the electronic configuration of carbon. Okay, we can see that it has 6 electrons in total, and that is true, as carbon has 6 electrons as well. Moving on, we can take a look at another element that is a bit more complicated. So for example, we can look at chlorine. So for chlorine, we have a period 3 element, right? So it corresponds to period 3 and it ends off with P5. In other words, we know that we can actually write until 3p5. So here's another example for chlorine. We know that we have to write until 3p5. So we will just fill up the previous orbitals to the maximum. And when we reach 3p5, we know that we are done, we have reached the configuration of chlorine. And as we can expect, there's a total of 17 electrons, which is true for what we see for chlorine. Okay, so this will work for your S block and your P block very effectively, but for the D block, which is actually your transition metals, we will need to do a slight adjustment. This slight adjustment is because of the fact that we fill up 4 S electrons first. Okay, so instead of writing like this, where we say this is period 1, 2, 3, and 4, right, and this we'll expect to be D1, D2, so on and so forth until D10. So for example, for titanium, if you are using this shortcut, you actually say that, okay, this ends at 4D2. However, we know that we fill the 4s electrons first, followed by 3d electrons. So what we're actually referring to this 4 is actually the 4s1 and the 4s2 here, followed by 3d1 and 3d2. So for titanium, it actually ends at 3d instead. Okay, so we can say that for titanium, we're going to write down 3d2, and we are just going to fill up everything else to their maximum before that, and that tells us the electronic configuration of titanium. So that's the first exception. For transition metals, we will actually write one number short of the actual period. Okay, and the reason is because we have to first fill up the 4s electrons before the 3d electrons. Okay, so here's another example. If we are going to fill up, for example, iron, right? So iron is right here in the middle. And iron is a D1, D2, D3, D4, D5, D6 system. So we should expect iron to end with D6, right? So instead of writing 4D6, right, we'll actually write 3D6. Okay, so we'll just fill up iron until we reach 3D6. Okay, so here's how we can actually think of writing this in an exam. We'll first write down the last one, 3D6, and we're just going to fill up the rest before that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and the 3d6 that we have already derived. So in this manner, we can actually write out electronic configuration much faster because we kind of know what the final state will be, right? So we just need to write until that particular electronic configuration. So let's just take a look at a few of these elements, right? So for calcium, it will end as a 1, 2, 3, 4. It will end as a 4s2. Okay, so we just write until 4s2, we will reach calcium. For phosphorus, we will just write until 1, 2, 3, 3p3. Right, so that is how we can write for phosphorus. For aluminium, it is 1, 2, 3, 3p1. So that's how we can write for aluminium. For nickel, it is D1, 2, 3, 4, 5, 6, 7, 8. So it's a 3d8. Okay, so that's how we can imagine for nickel. Okay, so that's the way we can actually use this as a shortcut by just looking at where the element is in the periodic table to figure out where the valence electrons are held in, and then we'll just write our electronic configuration until that particular orbital. Okay, so take note of the exception, which is your transition metals, and also take note for another exception, which is your chromium and copper. So if you are following this, then chromium should have a D4 system, but we know that chromium does not, because chromium prefers to have a 4s1, 3d5 instead. What about for copper? Copper will also not have a 3d9 system, it will actually end up with a 4s1, 3d10 system instead. And that's because by having a half-filled 3D subshell and a fully filled 3D subshell, it is actually more stable for chromium and copper. So these are the only two exceptions we have to pay attention to when we are using this as a shortcut. Okay, so other than that, that should help you save some time when we are thinking of all your normal elements. Alright, so hopefully you found this helpful, and thanks for watching this video.